In the last lecture, we derived this expression of entropy in the differential form as a function of u v n. So, what we are going to do is we are going to make use of this and develop an equation of state for a simple example. So, this is an example. So, for a pure fluid, the fundamental equation is given as S is equal to A u v divided by n and B n cube u n v. Okay. So, this is something which is given, and what is being asked is to obtain the equation of state P as a function of V and T for this material, where A and B are positive quantities. Okay. So, this is greater than 0, greater than 0. Okay. So, what we are going to do is we are going to make use of fundamental equation, the equation which we have derived here. Okay. So, we know this S as a function of u v n. Okay. So, we can write ds in differential form, and since ds is already given here, okay, so you will have ds as del s by del u for constant v n du and so forth. So, this will be your 1 by t, and this information we can make use of it here. Okay. This will be your a v by n plus b n cube u square v, and similarly p by t, which is this part, can be written as in terms of partial derivative with respect to v at constant a, and this is given by a u n plus b n cube u v square. Okay. So, now with this equation you can take the ratio of this p by t divided by 1 by t, which is nothing but p, and this can be now written as a u by n plus b n cube by u v square, and this is a v by n plus b n cube u square v. This, after rearranging, you should be able to get u by v. Okay. So, in other words, u is nothing but p v. Okay. You can plug in here this information on the right hand side. We get p by t as a p v by n plus b n cube p v cube. Okay. So, we can write in terms of molar property. Okay. So, if we consider molar property as v by n, okay, this would be b p v by n cube. Okay. So, sometimes it is also written as v underscore bar. Okay. And in that case you can write p as this equal to bt, or p is okay. So, this is your basically the equation of state based on the fundamental equation which is given to us. Okay. So, now we move on to a multivariate calculus. Multivariate calculus is nothing but a mathematical tools for deriving relationship between thermodynamic derivatives. So, what we are going to consider is let us say x, y, z and w as a kind of a variable. Okay. So, this is the variable which we are going to consider as well behaved functional relationship between them. So, for simplicity, and without loss of generality, we will assume that among the 4 there are 2 independent variables. Okay. Any 2 of them can serve independent variables. Then the following general mathematical relations can be used often in manipulating derivation of the functions, okay, which are commonly used in thermodynamic, in classical thermodynamics. So, the mathematical relations we are going to make use of it often are the inversion relation, which is nothing but del x by del y z is 1 by del y by del x z. Now, note that this is the partial derivative, or this is x equal to y z is being differentiated, whereas in this case y is equal to as a function of x z is being differentiated. Okay. Now, in addition to inversion, we will be often using commutation. Okay. And this can be written as del z, del square z, del x and del y. Okay. And this can be rearranged also, this sequence of derivative as del y by del y, del z by del x, the constant y, and here this is constant x. Okay. So, this is a commutation expression. Now, chain rule is often used. So, del x by del y at constant z can be written as del x by del w at constant z and del w by del y at constant z. This is by making use of inversion rule here, we can also write as del x by del w at constant z divided by del y by del w at constant z. Okay. So, this is the inversion rule. Now, in addition, you have this x y z minus 1 rule, which is nothing but a cyclic permutated derivative del x by del y by del z x. So, what we are doing is basically nothing but x y z, here it is y z x, and that means del z by del x at constant y, this is nothing but minus 1. Okay. So, these are the 3 important mathematical relations which we are going to often use it. So, let me now move on, okay, and now we consider case. In order to understand the dependency of the path, let us assume the function f0, which is a function depends on initial, a function which is basically nothing but let us say a state variable, or in general this could be a property. So, basically f0 is nothing but the function value at x0 and y0, and we are going to consider f1, which is a function value at x1 and y1. And what we are interested is f1 minus f2. Okay. This is a commonly occurring instances in thermodynamics. So, this can be evaluated by integrating df from x0 y0 to x1 y1. Okay. Now, we can write this in partial derivative form and as follows. Okay. So, we can write as del f by del x at constant y dx plus del f by del f constant x dy. Okay. Or in other words, you can also rewrite this as del f by del x y dx, and this integration is along this path, plus del f by del y constant x again this integration is along this path. Okay. That means sum of these two integral is independent of the path, because f depends on the initial and the final information. So, that is you are taking the difference of the functions at different point on your phase space, and thus left hand side is just depends on the initial and the final values, whereas the right hand side individual components does depend on the path, but when you add it up it has become independent of the path. You can understand from the point of view of du, if we can integrate along a certain path, this could be written as del u del w, and this would be delta u delta q minus, let us say if PV work is there, then P dV along this path gamma, okay, and this will be your del u, okay. This will be your delta u, which will be u2 minus u1. Okay. Left hand side does not depend on the path, but this depends on the path, okay. And thus in order to achieve the same delta u, and this will have to complement with each other in order to achieve the same. So, one can see that this particular work will depend on the path you are going to consider. For example, you can have this PV, and essentially the initial state is here and final state is here. So, this could be a one particular path, okay. Let us say my gamma 1, and there could be another path, and there could be another path here. This will be gamma 2 and gamma 3, okay. Now, naturally this is the area under the curve. So, of course, the value does depends on what particular path you are going to consider. For gamma 2 the work is more, gamma 1 the work is less, gamma 3 the work is further less, and thus this value depends on different gammas. On the other hand, delta q will have to also vary in order to maintain the same u2 minus u1. Okay. So, this is just a simple example to understand these functions. So, let me end this lecture, and we will continue this mathematical calculus review in the next lecture as well. Okay. So, see you in the next lecture.